Hello and welcome to the fourth video in this mini-series at the higher maths level on exponentials and logarithms. And in today's video I'm going to finally introduce the logarithm function. And what I'm going to do here is focus on motivating the logarithm function by talking about the inverse of a function. This is something that we've covered in a former tutorial, and I'll put a link in the description to this video to a previous video on inverse functions. But that really, I think, is an important thing to motivate the subject of logarithms. In my experience, students find the logarithms topic quite difficult. It can seem rather abstract. I think to help get away from that feeling of it being abstract, let's just quickly remind ourselves of the concept of the inverse function. So going all the way back to thinking about functions as a mapping from one set to another. So if I have a set of real numbers that I call x, and a particular member of that set I'll call little x, and then I have another set over here, the range as it were, and another element here which I'll call little y. Okay, and then the mapping that takes us from this x here to this y takes us from this element to this element of this set. We call that mapping a function, and we call it f of x. And we would say that y equals, or y arises from applying the mapping f to the element x. Now, you can ask the question, how would we return? How could we retrieve x from knowing y? And that's the concept of the inverse function. So going in reverse, we have this inverse function which we call f minus 1, and in this case we would say that x arises from applying the inverse function f minus 1 to the element y. Because applying the function and then applying the inverse function takes you back to the same point, or alternatively applying the inverse function and then applying the function takes you back to the same point in terms of this set theory way of thinking about functions, we have these very important relationships. We have that the function of the inverse function of x is equal to x, and likewise the inverse function applied to a function of x is equal to x. And the use of x in these two important relationships here is really just saying some number that the functions are being applied to. It's very easy to get confused about a particular x in, say, this diagram or on an xy coordinate axes, but when we use x typically with functions, we're really just using that as a symbol to say a number that the function is being applied to. So the way to think about this is that given a number, if I apply the inverse function to that number and then apply the function to that outcome, I will get the original number back. You can think about it as this is an object, perhaps like a gift that's been wrapped, and then you're unwrapping it, and then you're rewrapping it, and you get back the original wrapped gift. Or here, for example, it's like saying that I have an object that I'm wrapping, and then I'm unwrapping it, and I get back the original object. So that's the very important relationships that relate the inverse function to the original function. And we're very familiar with this idea, but we don't often recognize that we're very familiar. So let me just give you some very simple examples of functions and their inverses. And this will motivate then the logarithm. So for example, imagine we have a very simple function, doubling. So we take a number x and we double it. So this mapping would say take the number 7 to the number 14. Now how would we get back? How would we go back from 14 to 7? Well, that would be the halving function. And you can see, in terms of these relationships here, that, for example, doubling a halving gives us back the original variable, or alternatively, halving a doubling takes us back to the original variable. Another example would be the square function. If I take the number, let me take the number 7 again and square that to 49, then the question would be, how do I undo that? How do I get from 49 to 7? The inverse of the squaring function is the square root function. And again, we can see here that we would have applying the squaring function to the square root function just returns the original function, or alternatively applying the square root function to the squaring function returns the original variable. So when we come to think of the exponential function, a to the x, we can say, well, what undoes that function? What's the inverse of that function? And by definition, that's the logarithm. So if I have an exponential function with base a, to undo that function, the inverse is the logarithm to the base a of x. It's an unfamiliar symbol, just as this square root sign, when you first encounter it, at some stage in earlier school years, is an unfamiliar symbol. But this log to the base a literally means that thing which undoes the exponential function. A particular example, of course, of a base, the most important one, is the number e that we talked about in the previous tutorial. When we have the exponential function to the base e, you could write this as log to the base e of x, but because that's so common, as I say, probably 95% of exponentials in science and maths are using the base e. Because it's so common, we don't have the fussy symbol log base e. We use a shorthand. We write ln of x, which literally stands for log to the base e. So ln or ln is the inverse function of the particular case of the exponential e to the x, and it's a shorthand for log to the base e of x. Very good. And let's now see, very, very importantly, what does that look like in terms of these relationships? And these are really important now. So what does that look like? Well, what we're saying is that if we apply the exponential function, so a to the power of its argument, and the argument is the inverse function, which is log to the base a of x, then this returns x. So to the base a, the exponential of log to the base a returns the argument of that logarithm. That's a very important and useful relationship that connects exponentials and logarithms. Similarly, if I apply the inverse function, the logarithm, to the base a, and I apply that to the forward function, the exponential, then again it returns x. So these two relationships, they look quite complicated, but they're really exactly in the same, they're the same concept as these much more sort of straightforward relationships. It's a little bit unfamiliar, but with enough practice of exponentials and logarithms, you'll see that these are very natural expressions and very useful expressions. So that's then talking about inverse functions, and let's just get a sense of this graphically. So let me sketch an exponential function, and then let me sketch the logarithm function as the inverse. And if you remember graphically, if we want to sketch an inverse function, we need to reflect the function about the diagonal. So let me sketch on here a diagonal, which is really just a line y equals x. And reflecting a function about this line automatically generates the inverse function. Okay, so this is just the line here, y equals x, and we're thinking of that as a mirror. And now if I think of the exponential function, remember the exponential function a to the x. When x is 0, I have a to the power of 0, which is 1. So the exponential function is going to pass through this point 1, 0. 0, 1, I beg your pardon. And when x equals 1, the exponential function will be a to the power of 1, which is a, and we'll take a greater than 1. So we'll take this to be a here, some particular base. And so my exponential function has to pass through these 2 points. Let me just remind you of that then. So a to the power of 0 is 1, and a to the power of 1 is a. So let me just sketch that exponential function. Has to pass through those 2 points. We know it decays very rapidly on the negative side of the origin along the x-axis there, and then it's quite hard to sketch this at this angle, but let me try my best. Very rapidly increasing function. So this is the function y equals a to the power of x. Now the inverse is the reflection of this line about the diagonal. So reflecting these points here, this point 0, 1 gets reflected to here, which would be the point 1, 0. I'm just going to try and leave a little bit of room for the actual function there. There's the origin. And then this point will be reflected to here, so it's going to be, it's about here, isn't it? This is a now. Gets reflected to there, and this is the point a, 1. And this was the point over here, this was 1, a. So the inverse of the exponential has to pass through these 2 points. And let's just note that here. So because that's true, we have that log to the base a of 1 equals 0, and we have that log to the base a of a equals 1. You see how we're undoing these functions. So the exponential takes 0 to 1, and the logarithm takes us back from 1 to 0. The exponential function takes 1 to a, and the logarithm function goes backwards and takes us from a to 1. And that function, what does it look like? Reflecting this very rapidly decreasing tail of the exponential here will look like this. And then this very rapidly increasing function of the exponential for positive x, when reflected, will be an extraordinarily slowly increasing function for positive x. And this function then, the inverse, is what the logarithm function looks like. So that's a plot of the logarithm function. The really important thing to always remember about the logarithm function is that it has the value 0 when its argument is 1, and it has the value 1 when its argument is the base of the logarithm. It's always negative when the argument is less than 1, and it increases extremely slowly. Its slowness of increase is of the same degree as the rapidness of increase of the exponential. Right, so I think that might be all we need to say in this particular tutorial about motivating the logarithm function from thinking about the inverse of the exponential function. I really want to stress these two relationships here, which are clearly identifiable as the inverse relationships of these exponential function relationships here, but these are sort of important compass points for you when you're thinking about logarithms. That the logarithm to the base a of a is 1 and the logarithm to the base a of 1 is 0, that follow directly from thinking about the logarithm as the inverse function to the exponential. One last thing to mention, given that we are talking about the Scottish curriculum here, is that logarithms were essentially devised by a Scottish man back in the 16th century going by the name of John Napier, who was resident in Edinburgh. And I don't know much about the history of this, although it is fascinating that Scotland was sort of the home of logarithms. In the next tutorial, we're going to be talking about the laws of logarithms, or the rules of manipulating logarithms. And what you'll see from those is that logarithms are incredibly useful in simplifying complicated arithmetic. And that was much of the original motivation for logarithms, was to aid in doing complicated sums, well, of course, before the time of mechanical or electronic calculators, when people needed to do complicated calculations because they wanted to work out whether it was astronomical or various trigonometrical results, and sometimes that involved very complicated arithmetic. And logarithms massively speed that up, as we'll see in the next tutorial. So I hope that was helpful, and I will see you next time.